let's do a review of simple harmonic motion here. So one skill unit. So simple harmonic motion, often abbreviated SHM there. This is just repeated motion over and over and over again. That's one point that you need. A second point is that you need a restoring force, which means it's got to be towards the equilibrium position there. And the third thing that we need is the force needs to be proportional to x. So proportional to your distance from the equilibrium point. So two good examples of simple harmonic motion are a mass on a spring, 100% that's simple harmonic motion if it's an ideal spring, and then a pendulum. As long as our angle is less than 15 degrees, then the angle doesn't really affect the period at all. And so we've got equations for each of these cases here. So for a mass on a spring, it looks like this. The period of a spring is 2 pi radical m over k. And we also have an equation for a pendulum, and that is the period of a pendulum is 2 pi radical L over G. So a few things to note here. One is for the spring, that the period of the spring does not depend upon an amplitude, which a lot of people would guess. So if you imagine, well here, let's actually put up a picture, that we've got a mass sitting on a frictionless surface there, and right here is the equilibrium point. And then right here, can I squeeze it all in? There we go. So then we push it in some distance a from that equilibrium point, and we time how long it takes to go all the way over and back. That time will not depend upon how far back you push it. But in some people that's counterintuitive, like, oh, you push it further back, it's gonna take longer. But the thing is, because it's a spring, the further back you push it, the harder it's pushing. And so that will counteract that. So the period of a spring or a pendulum, it doesn't matter how far back you pull it. So it doesn't matter how the angle you pull it back or how far you compress it. Another thing to keep in mind with the period of a pendulum is that it's only proportional to the square root of the length. So one thing is it's not proportional to the mass. It doesn't matter how much mass you put on there for a pendulum. It definitely matters for a mass on a spring, because this thing has more inertia and would be harder to push. And it also doesn't depend upon the angle. That's kind of like saying that it doesn't depend upon the amplitude there. So those are the basics of it right there. Mass doesn't affect it for a pendulum, and that's because it's being pulled on with more gravity, but it has more inertia, and so those two effects cancel out here. Let's focus on the spring examples, although this would apply, these graphs I'm about to show you, for a pendulum as well. So let's remove these and then get these out of the way, and put a few more examples up here with this spring. So it was here, we compressed it to a distance A right there. The A will stand for the amplitude, the maximum distance. It will start to come back, so it'll get back to the middle like here, and then it will overshoot it a certain distance. If we called this distance A, then this distance here to the right would be negative A. So I know that's counterintuitive, I made to the left positive, but whatever. So it would go the same distance if there was no friction and this was an ideal spring. And then it would come back to the middle, and then it would go back to there. So it goes here to there, back to here to there. So a few things to note about this. One thing is, let's focus in on the middle right here. So let me move these down for a second and move this over here. What are some things that we could talk about in this middle position here? And what's a maximum and what's a minimum? Well, right there in the middle position, has been pushed from here to here. The moment it passes that middle position, it's going to be pulled back the other way, so it's going to start to slow down. It's been speeding up until this point, but then it's going to start to slow down. So its velocity is a maximum right here at the equilibrium point. That means, by the way, its kinetic energy is a maximum, and if they ask it, which they probably won't, but just in case, its momentum is a maximum here at the middle point as well. These following things are minimums. The minimum is the position, because we define the position here at the equilibrium point to be 0. So no position, and therefore no force. Why not? Well, let's review quickly. Hooke's law tells us that the force of a spring is equal to the spring constant times the stretch distance. So if we have no stretch distance, we have no force. If the force is 0, then the acceleration must be 0. Why? Newton's second law. If the acceleration is 0, if the force is 0, then the acceleration is 0 as well. And then the spring energy must also be 0. Why? Well, let's put up the energy equation for a spring. If we have no stretch distance, we have no elastic potential energy in there either. Now, what if we were talking about out here on the ends? Then all of these things get flipped. Out here on the ends, we have a minimum. In other words, the velocity is 0, and the kinetic energy is 0, and the momentum is 0. And what are maximums out here on the end? Well, the distance is a maximum, and therefore our force is a maximum, and therefore acceleration is a maximum, and therefore our elastic potential energy is a maximum, actually, because of the distance being a maximum there. So that is what to keep in mind with these position graphs. Now, let's go and put another graph up here, actually. And let's pretend that we were tracking this thing's position as a function of time. So again, we put up here this mass, we push it back a distance a, we let it go from here, we started the timer, and then we tracked its motion. So here's a graph of its position versus time. And so notice we get a cosine curve in this case. Why a cosine? Because I started it out on a maximum position here. So then you get a cosine graph. So here it's at the max position. Here would be when it reached the equilibrium again. This right here is when it is at the maximum position on the other side. And then we come back to the middle and then back to our position over here. And that time right here would represent one full cycle. So the time from here to here would be the period. And if you have the period, you can also get the frequency by flipping it around like that. There is an equation that tells you what that should look like, and I just realized I forgot to make a card for it, so let me just write it right now. That equation looks like this. Our position as a function of time is our amplitude, whatever that value is, times whether it's a cosine or a sine graph. Here you can see it's a cosine graph because we started at a maximum position. And then in parentheses we put 2 pi our frequency. And again, we could get our frequency if we realized the time from here to here was the period. We could flip that to get the frequency. And then t. So this allows us, if we know the time, we can plug it into this equation and get our position at any moment in time there. If this is the position versus time graph, what does the velocity versus time graph look like? Well, right here, we're starting from 0 speed. We're right out there at the maximum edge there, so we have no velocity. And we are headed back towards the middle point, back towards the left side there, the way we set up our equation. So this would be heading in a negative velocity there. So notice right when we get to the 0 position, we are at a maximum velocity. And since I'm traveling in the negative direction, I've got a maximum negative velocity. Then this is when we are in the middle, and then as soon as we overshoot it, we start to be pulled on and slow down. And so then we stop for a moment in time right here. Notice when we stop again, when our velocity is 0 again, we are at our maximum negative position. We're all the way over here now on the other side. And then we start to pick up speed to the, in this case I call it to the left, remember positive, back to the left. And so we reach a maximum speed right when we're at the middle position again. So once we get back to the middle position, but we're headed this way, we will have a maximum positive speed. And then we'll start to be pulled back to the left and we'll slow back down, and right when we get to 0 velocity again, we'll be back to the maximum position on the other side there. So if you know your calculus, the derivative of this graph will give you this graph here. So now what would the acceleration versus time graph look like? So here is our acceleration versus time graph. Oh, cut off. Here, let's put it up here. And I'm going to move the position out for a second so that you can line it up with the velocity versus time graph. So this graph is the derivative of this graph, but you don't have to worry about it. That's to say that we're graphing the slope of this graph to get this one. Here, when we have zero velocity, remember we started out at the maximum edge here. We started right here. And we call to the left negative in this problem. So over this way, it's going to be pushed with a maximum force and a maximum acceleration, but to the left, or excuse me, to the right, so it's negative. So we start with a maximum negative acceleration. Another way to think about it is the maximum negative slope occurs right now, and the slope of this graph is acceleration. Here, when we get to the middle, we're at our max velocity, but we don't have any push or pull in the middle, and so our acceleration is equal to 0 there. And then we get to the far edge, so now we're back over here. We've stopped for a moment in time, no velocity, but now we have a maximum pull and a maximum acceleration back to the positive direction. So now we have a positive acceleration there. And then when we get back to the middle here, we are back to 0 acceleration here. And then we repeat the cycle over there. So knowing how to do all three of those graphs, position versus time, acceleration versus time, and velocity versus time from each other is an important skill to know how to do with simple harmonic motion. So let's do one more set of things here and look at some other graphs. Let's say we wanted a graph of the energy versus position. That would look like this. So on this graph, I have 3 lines. Now, what do the 3 different lines mean? Let me get my key out here. So the orange line is the spring energy, the green line is the kinetic energy, and the purple line is the total mechanical energy. So notice out here on my maximum edges here, I have maximum spring energy. That makes sense because this is the equation for our spring energy. So when x is a maximum at our amplitudes, our potential energy is a maximum. This equation is also, because it's squared, what lets us know we have a parabolic shape right there. The kinetic energy will just be the flip of that. So we'll have 0 kinetic energy out on the amplitudes, but a maximum in the middle. The two together always have to add up to the same total mechanical energy, because if we don't have any friction, assuming, then we're not going to lose any of our energy as we slide back and forth. And it will go down this way and back, down this way and back. And same thing with kinetic energy there. You might also see a graph that is not energy versus position, but energy versus time. So in this case, one important thing to notice, it looks very similar, is that we do not have any negative values here, because energy in this case won't be negative. So this is not a sine graph. It's actually a sine squared graph, which looks pretty much the same. And the reason for that, again, is because if this is our graph of position versus time, to graph the spring energy, it'd be our position squared. And so we'd square this. So this side would come up here and be positive as well. So if this was like 1, 2, 3, and 4 seconds, then as we came up here, we would actually double our peaks. This would be, if this was 0 seconds, we start at a maximum spring potential energy there. But down here, when we're in our negative position, that's when we be back up to our maximum spring energy again, because the spring energy doesn't care if you're positive or negative. And so again, if this was 1 and 2 seconds, then this would be back to 2 seconds right here, and this would be at 1 second. At 1 second, we have no position, so we'd have no spring energy there. So that would be the orange, again, the graph of the potential energy, the elastic potential energy versus time, if I started out on the edge. The flip of that's the kinetic energy. So again, kinetic energy is also a squared graph because it's velocity squared. So if we took our velocity graph and squared it to get the kinetic energy, it has no negatives either because this gets flipped up. And so the other thing is just to think it's got to be the flip there. So the green one there represents the kinetic energy versus time. And then just like before, the total mechanical energy would be this purple dashed line. That shouldn't be changing at all over time. It should be a constant. Now, one thing they might put in there on you is that what if there is some friction, right? If there is friction, then slowly this energy is going to die out, and then it's going to look something like this. So then your total amount of energy is slowly going to die out like this. The exact shape of this doesn't really matter. They're not going to get strict on you on that. You can study that if you study mechanical engineering. But notice our our spring potential energy keeps getting less and less and less each time because friction doesn't allow us to get all the way back out there. And it keeps slowing us down in velocity as well. They won't get deep into this other than just to realize that if there's friction, your energies will taper off with time.